you can see that these resistors have basically they have a value. The value of this resistance is 100 ohm, 100 ohm, and 100 ohm. Now, there is something which needs to be understood here. There is something called tolerance. There is something called tolerance, and there is something called tolerance specifically related to resistors. There is something called the number of significant figures. There is something called the number of significant figures, and then there is some rules regarding these significant figures. The laws of significant figures. I'll point out these very, very briefly. So basically, the number of significant figures it's of course a very simple concept. I'll tell you about them in just a few moments. Okay, so basically the number of significant figures is basically, in electronics, you do all kinds of measurements. I mean, the electronics is just simply a bunch of measurements put together, and then you do some calculation on them, and you do different things, but everything that you do in electronics, they are almost always involve measurement. Now, any sort of measurement that you do contains some digits of numbers. Now, these digits of numbers are measured, of course, meaning that, for example, when you have a power supply and when you put a voltmeter across that power supply, to measure the voltage of the power supply, you are measuring that voltage. And then, for example, you have a digital multimeter, a digital voltmeter, or a digital or one of those analog meters, and then depending on the type of meter, for example, the needle goes across the scale, or you see some digits on the screen, and then you will get some number for that measurement. Now, suppose that you make some measurements of a voltage, and your multimeter tells you that this voltage is 12 point, for example, 126, for example, 126 volts. Now, since you have measured all of these digits, since your multimeter has actually measured all of these digits, then basically all of these digits are, of course, measured digits. And since they are measured digits, they are all significant in this measurement, or they are all significant in this number. And therefore, you can say that, for example, this number has 5 significant figures, 1, 2, 3, 4, and 5. And of course, in all kinds of measurements, basically there is the same concept, meaning that, for example, when you take a meter stick and measure a length, then you will get, for example, 2.3 so for example, let's say that you get, for example, some number, for example, like 123.5 meters, for example, for example, 123.55 meters. Again, all of these digits that you have here are all significant, because you have seen and you have measured the digit in the hundredths place, you have seen and measured the digit in the tens place, you have seen and measured the digit in the ones place, you have seen them and measured the digit in the 1/10th place, because your meter stick is graduated to 1/10 of a centimeter, or actually this is supposed to be, for example, centimeter. What I meant to say is centimeter. To 1/10 of a centimeter, which is 1 millimeter, and then suppose that you estimate the last digit to 0.05, and then you will get 123.55 centimeters for that measurement, and so this measurement would have again 5 significant figures. And of course, you understand that this last digit over here, since you estimated that this is an estimated digit, and therefore it is, but still it is significant. The last digit always is estimated, but it is always significant. And even in your multimeter, the last digit is always estimated, but it is again significant. And even when you read an analog scale, the last digit is always estimated, because you have to read between two of those graduations, and between those two graduations there is no graduation, so you're estimating somehow that this is, for example, halfway between these two graduations, and so this is, I take this as 0.4, 0.5, or 0.04, and depending on the range, and so that last digit is going to be also estimated, but again this is significant. So depending on the resolution of your measurement device, you will get some digits after the decimal point, and well, all of those digits will be significant. And that's all about significant figures, right? So then there is other concepts here, but I guess we don't need to talk about them right now. Then there is also the problem of tolerance. There is also the problem of tolerance, and there is one more thing that I need to talk about when it comes to measurement. And any measurement, this is very important, any measurement always contains some uncertainty. Every measurement always contains some uncertainty, meaning that basically, depending on the measurement device that you have, for example, you have a meter which is for example 5 years old. You bought this meter, for example, a multimeter that you bought 5 years ago, and then you have been working with this meter. It's an analog meter. You have accidentally something, a wire cutter or a screwdriver or something has fallen on the needle, for example, a couple of times. It's fallen down a couple of times, and it's old. It's not been calibrated since the last time since in 5 years time, and so on and so forth. So you could say that, for example, this meter has, for example, 5% error or 5% uncertainty, meaning that any reading that any measurement that you make with this multimeter has 5% at least uncertainty, meaning that, for example, when you read 10.5, for example, volts, this 10.5 volts, you cannot think of this reading as exactly 10.5 volts. The actual voltage that you're measuring, so this would be 10.5, this would actually be 10.5 plus or minus 5%, all in volts, meaning that if you calculate 5% of 10.5, so that would be 5% of 10.5 times 5% times 5% is about 0.0525, because 10% of 10 would be 1, so 0.525. Okay, so basically 0.525 is 5% of 10.5. 0.525. That means that the actual voltage, the actual voltage that you are measuring is somewhere between basically 10.5 minus 0.525 volts and 10.5 plus 0.525 volts. 0.525 volts, which is the same thing as, well, let's say 10.5, 0.525 volts would be 52011. This I added, so this would be 11.025. 11.025 volts, and 10.5 minus 0.525, that would be basically 0, 9, 0, 10, 9, 15, 14, 9 and 10, and then you have 5 over here, 7, and 9 plus 5 is equal to 14, and 9. So that's 9.975. 9.975. 9.975 volts. So the actual voltage, if I call it, for example, V1, your V1 is actually any voltage between 9.975 volts and 11.025 volts. So that's basically the meaning of uncertainty. And these uncertainties, if the application is important, of course you have to basically take them into consideration in your calculation and in your design and whatever it is that you're doing. So that's about, so basically you have the significant figures, that's what you measure, which is basically this measurement, and with this measurement comes some uncertainty, and this is the uncertainty, for example, 5% or 10% or 3%, and so on and so forth. And also the same thing applies to, for example, these to a resistor, for example. So for example, you have seen that the resistor has a tolerance of 2%, 5%, 1%, and so on and so forth. Which means that, for example, a 10 ohm resistor could be anywhere between, if it's a 5% tolerance resistor, then basically divide by 10 would be 0.1. So 1% of so about 0.5 ohm, basically you get less or more than basically 10 ohm in a 10 ohm resistor if it's a 5% resistor, and so on and so forth. So you need to take care of those in your design. And now when you have the number of significant figures in your measurement, then what you need to do is that in calculation you need to basically take care of those significant figures. For example, when you have when this current is 2.0 amp, when they write this as 2.0 amp, what that means is that this current is different from just a simple 2 amp current. This 2 amp current has only one significant figure, meaning that the last digit meaning that the only digit actually that was measured only was the ones place. But with this current, the ones digit was measured, also the 1/10th digit was also measured, and therefore this is actually measured digit. This was actually a measured digit, and therefore this has two significant figures. This has only one significant figure. Now when you use these measurements, or when you use these values in calculation, we do what we do is that we add or subtract, or we multiply and basically divide. So there are basically four things that we do in calculation. There is addition, subtraction, multiplication, and division. Now, if we categorize these four main operations into two categories, meaning that if you put addition and subtraction together, if you put these two together, and if you put multiplication and division together, then there is two rules for when it comes to significant figures. So suppose that, for example, you have basically 2.0 amps and 1.0 amps, and you are adding them together, right? So you have 2.0 amps and 1.0 amps, and you are adding them together. So you get 0 plus 0 is equal to 0, 2 plus 1 is equal to 3, 3.0 amps. Which means that the result is going to have the number of decimal places as the number with the least number of decimal places. Meaning that, for example, suppose that I have a current of 2.056 amps, and I have another current of 1.62 amps, and I want to add these two together. So that would be a 6, that would be a 5 plus 2 is equal to 7, a 6 and 3.676 amps. But then, since this number has only two decimal places, not significant figures, 2 decimal places, that means that basically this number can have only 2 decimal places, not more than that. And so you have to round to this digit, which means that this number becomes 3.68 amps. 3.68 amps. right? Not 3.676. This much resolution you just don't have because this number didn't have that much resolution in the first place, right? Or at least one of the numbers didn't have that much resolution in the first place. So in the result, you get the resolution of the number with the least amount of resolution, basically, which becomes 3.68 amps. So this is about addition and subtraction. So very simple. Now, when you do basically, of course, all the time, or most of the time, we do multiplication and division. So for example, you have V is equal to I times R, and your voltage is equal to current times resistance. Suppose that you have a resistor that is, for example, you measure the resistor, the resistance of that resistor using a multimeter that shows you the resistance all the way up to 1 milliohm, for example, to 1 milliohm, and then it tells you that the resistor is actually, for example, I don't know, 230.135 ohm. That's your resistor. And you have a current going through this resistor, which is, for example, I don't know, 0.35, for example, 2, for example, amps, 352 milliamps, for example. Now, when you want to calculate the voltage across this resistor, V is equal to IR would be 230.135 times 0.352, and that would be, if you use a calculator to calculate this, you will get a bunch of digits, a lot of digits actually, 230.135, and multiply that by 0.352, and you get so many digits here. So you get 8, you get basically 81, you get 81 point, for example, 00752 volts. That is the voltage across that resistor. But then since this number has 6 significant figures, and this number has only, and basically one thing about significant figures is that this number has only 3 significant figures, because this 0 is not regarded as a significant figure, and I'll tell you why that is. Which brings us to the story of scientific notation. But for now, let's just suppose that this number has only 3 significant figures. This number has 6 significant figures, and therefore this number that you have gotten in calculation from these two numbers, and basically this number can have only the number of significant figures of the number with the least number of significant figures. So here I have 6 significant figures, here I have 3 significant figures. The least number of significant figures would be 3. So you have to basically round this number to 3 significant figures, which means that you would get, this is 1, 2, and 3 significant. You have to round this number to the 1/10th place, which would give you basically 81.0 volts. And the rest of the digits are just garbage in this case, because you don't really, I mean, that much resolution you cannot have, because again, you didn't have that much resolution in the first place. Okay, so your voltage becomes that. Now, about why this number has only has three significant figures, although there is a 0 over here, and I'm not counting this 0. The reason for this is that this 0, when I write 0.352, this 0 is just a placeholder, okay? And you could also have a number like, for example, 352 and 3 zeros here, and this number could also have the same story, meaning that I could tell you that this number has only three significant figures, and these 3 zeros are just simple placeholders and not significant figures. Or they could also be significant as well, but that's another story, we will talk about it. But now coming back to this number, you see that this number, if I move the decimal point to this, to between 3 and 5, if I move the decimal point to between 3 and 5, I could write this as 3.52 into 10 raised to the power negative 1. 3.52 into 10 raised to the power negative 1, and it's again still the same number with the same value. If you multiply 3.52 by 10 raised to the power negative 1, meaning that dividing by 10, you would get 0.352, which is the same number. And now this number, when you count the number of digits in this number, you will get 1, 2, 3. So this number has 3 significant figures, and it's still the same number that we had before, which means that basically this 0 was just a placeholder to tell you where the decimal place goes. And if I didn't have to put the decimal place in the beginning of the number, I wouldn't have needed this 0 in the first place. Meaning that I could even write this number as 0.352, and I wouldn't even need the 0 over there. So, but because people might make mistakes, they put this 0 here so as to point out the fact that this 0 is there, and this number starts with a decimal point, right? Or you could have the same number as 0.000352, and still all of these zeros are placeholders, because you can still write this number as 3.52 into 10 raised to the power, for example, negative 4, and still you would have 3 significant figures, and the decimal place, and this part tells you where the decimal place goes. This is your placeholder, and this becomes basically your significant figures, which means that all of these leading zeros are always not significant. Now there is the problem of so these were leading zeros. These are called trailing zeros. These are called leading zeros. Leading zeros. And I don't know how to write zeros with an S. Without an E. So these are called leading zeros, and here we have trailing zeros. Here we have trailing zeros. Trailing zeros sometimes are significant, sometimes are not significant, depending on the situation. And as you can see, there is ambiguity with this type of number, and therefore, of course, we will of course talk about that as well. Okay, so about trailing zeros. Now, basically having the same number 352,000, for example. So you could have a number like, for example, you could measure something, whatever that might be, and for example, let's say that there is a number of people in a town, for example. So for example, there is 352,000, for example, 125 people in a town, right? Now, when somebody asks you how many people are there in this town, since it's a town, you would probably say about 350,000, or you would say about 352,000. You would not say, for example, you would not say exactly 352,125 people, because people do not care about the last 125 people. They want to know basically a rounded number, for example, to the last, for example, to the last 10,000 people, or to the last 1,000 people, and so on and so forth. More resolution they don't really need. So you would round this number to, in your mind, you would round this number to 352, and then since this is a 1 over here, you don't have to make any changes to this 2. You would have only zeros over here, and now these zeros serve as placeholders, or only as placeholders, to tell you that basically, to tell you that this is the ones place, the tens place, the hundreds place, this is the thousands place, and this is the 10,000 place, this is the 10,000s place, and this is the 100,000s place. Now, if these zeros were not there, and if you were to write this as just 352, then of course the number would not have the same value. This 2 would be in the ones place, this 5 would be in the tens place, and the 3 would be in the basically in the hundreds place, and of course that would not be the same number of people. Meaning that you could write this number as 352 times 1,000, or you could write it as 352 into 10 raised to the power 3. And now basically this 1,000, or this 10 raised to the power 3, is acting as the placeholder. But of course, when it comes to science, not particularly in electronics, people use milli, micro, kilo, and that sort of thing, but usually they don't specifically use the scientific notation unless somebody is doing very scientific work in electronics. Otherwise they don't do it. Engineers usually round things off without paying that much notation into the scientific notation and that sort of thing. When you get into physics and that sort of thing, then of course scientific notation becomes important. But but essentially, to basically indicate that this number has 3 significant figures, and to basically tell people about the placeholders, you could write this as 3.52 into 10 raised to the power 2 into 10 raised to the power 3, which becomes 3.52 into 10 raised to the power 5, right? So which means that these zeros over here, and now this tells you where the decimal place actually goes in this number. which means that these 3 zeros in this number are actually not measured and so therefore not significant, because you have rounded your number to the thousands place. And since you have rounded your number to your thousands place, these digits are actually now lost. You don't know what they were. They are just, and these zeros are just acting as a placeholder. That's all that it is. So that's basically about that. Sometimes the zeros are actually placeholders, are actually significant. Meaning that you measure something and you measure that quantity as exactly 352,000, meaning that you measure this digit, you measure this digit, you measure this digit, and this digit you measure it happens to be 0. You measure this digit happens to be 0, and you measure this digit happens to be 0. And then in order to indicate that these zeros are actually significant, you would write this number as 3.52000 into 10 raised to the power, for example, 5. And that shows that this number has actually 6 significant figures, and the decimal point is supposed to go over here because you're multiplying by 10 raised to the power 5, right? So that is basically, that is about that. Now, so these are called basically trailing zeros. We talked about leading zeros. So trailing zeros are sometimes significant, sometimes not significant, depending on the situation. And so you can use scientific notation in order to indicate how many significant figures you actually have in your number. And in scientific notation, one last note is that basically whatever the number that you might have, you write it as some a times 10 raised to the power b, for example. And this has to be some number between basically 1 and 10. This has to be some number between 1 and 10. As you can see, for example, I haven't written this as 35.2000. I have written it as 3.5 so that it becomes some number between 1 and 10, not greater than 10, not less than 1. This number is something between 1 and 10, and then this b is basically the exponent of 10 that shows you where the decimal place goes in the number. So that is about the scientific notation. And then there is, and these leading zeros are never significant. They are actually never significant. And there is something called a captive zero. A captive zero is always significant, meaning that, for example, if you have 3.302000, now these 3 zeros could be significant, could not be significant, depending on the situation. But this 0 is always significant. Is always significant. Because basically, of course you have measured this digit, and then basically in order for you, and this is the digit that you have actually measured, right? And in order for you to be able to measure this digit, first you have to measure this digit. That means that you have measured this 0, and the digit happened to be a 0. So there you have a 0, a measured 0, so it's significant. And then you have measured this 2, so far you have 3 significant figures. And then after that, whether or not you have measured these zeros or you have rounded your number, that's another story. But this 0, which is a captive 0, which is called a captive 0, is always significant because you had to measure this 0 so that you could measure this 2, and of course you have measured this 2, otherwise you wouldn't have that. And since you have measured this 2, that means that you have definitely measured this 0, and this digit happened to be a 0, and is called a captive 0 and is always significant.